Somewhere in a laboratory, cooled colder than deep space, scientists just watched a material do something that should be physically impossible. They took a strange metal, blasted it with a magnetic field 7 times stronger than an MRI machine, and instead of destroying its ability to carry electricity without resistance, the field killed that ability and then, at even higher strength, brought it roaring back from the dead. Physicists are now calling it the Lazarus phase, named after the man who came back to life, and it has forced researchers to admit that everything they thought they understood about superconductors was incomplete. This is not a small tweak to an old idea. This is a brand new category of superconductivity, one that textbooks never predicted, and theorists never saw coming. And it is quietly rewriting the roadmap toward quantum computers, lossless power grids, and technologies we have not even imagined yet. To understand why this discovery is such a big deal, you first need to understand what a superconductor actually is. Because most people have heard the word without ever grasping how strange the phenomenon really is. In an ordinary wire, electricity flows the way water flows through a slightly clogged pipe, constantly bumping into obstacles, losing energy as heat along the way. That is why your phone charger gets warm, why power lines lose a noticeable percentage of electricity over long distances, and why every electronic device wastes so mere fraction of the power it consumes. A superconductor breaks that rule entirely. Below a certain critical temperature, electrons inside these materials stop behaving like isolated particles bouncing around and instead form partnerships called Cooper pairs, gliding through the material in a coordinated quantum dance that meets zero resistance, no heat loss, no wasted energy, current that could theoretically flow forever once it starts. For most of the 20th century, physicists believed they had a fairly complete picture of how these Cooper pairs formed. In classic superconductors like lead, tin, and mercury, one electron spins up and another spins down, and they move toward each other head-on with no net rotation at all. Scientists call this S-wave pairing, and it was the first type ever discovered, back in the 1950s, explained by a theory so elegant it won its creators a Nobel Prize. Decades later, researchers found a second, stranger flavor in a class of materials known as high-temperature superconductors, where the electron pairs carry 2 units of angular momentum instead of 0. This became known as D-wave pairing, and it powered an entirely new era of superconductivity research through the 1980s and beyond. For a long stretch of scientific history, those were considered the only 2 real options, S-wave and D-wave, full stop. Then, physicists began theorizing about a third possibility that nobody had ever actually confirmed in nature, a state called P-wave, or spin-triplet superconductivity. In this exotic scenario, instead of electrons pairing up with opposite spins canceling each other out, they pair up with spins pointing in the same direction, parallel rather than opposite. This sounds like a small technical distinction, but the consequences are enormous. A spin-triplet superconductor would be far more resistant to destruction by magnetic fields than any conventional superconductor, and it could host something called Majorana fermions, ghostly particles that are their own antiparticles. Majorana fermions are considered one of the most promising building blocks for fault-tolerant quantum computers, because information stored in them is naturally protected from the noise and errors that plague every quantum computing approach we currently have. For over 20 years, one specific compound, strontium ruthenate, was the leading suspect for hosting this triplet state, and labs around the world chased it obsessively. Here is where the story takes its first genuinely strange turn. When Cornell physicists finally built equipment sensitive enough to test strontium ruthenate properly, cooling their apparatus down to just 1 degree above absolute zero using resonant ultrasound spectroscopy, they discovered the material was not behaving like a triplet superconductor at all. Instead, the data pointed to something nobody had ever proposed as a real possibility, a pairing state with 4 full units of angular momentum, a completely new category the team started calling G-wave. The lead researcher on that project put it bluntly, saying the experiment revealed the possibility of a new type of superconductor that scientists had never even thought about before, one that opens up the entire space of what a superconductor can actually be. If S-wave is 0 rotation and D-wave is 2 units, G-wave sits in territory so exotic that almost no theoretical framework anticipated it existing in nature at all. But G-wave was just the opening act. If you thought the story of unexpected superconductors ended there, wait until you hear what happened with a heavy, radioactive adjacent compound called uranium ditelluride, known to physicists simply as UTE2. This material was discovered somewhat by accident in 2019, and almost immediately it started breaking rules that had stood for decades. Unlike almost every other superconductor on Earth, which loses its special zero resistance property the moment you expose it to a sufficiently strong magnetic field, UTE2 seemed to shrug off magnetic punishment that should have destroyed it outright. Researchers determined it survives magnetic fields up to roughly 35 Tesla, more than 10 times stronger than most hospital MRI scanners, a threshold so far beyond ordinary superconducting limits that it forced physicists to reconsider what was even theoretically possible in a real material. Then, in 2026, the story escalated into something far stranger than mere resilience. An international team, including researchers from Rice University and the National Institute of Standards and Technology, discovered that UTE2 does not just resist magnetic fields, it actually loses its superconductivity around 10 Tesla, exactly the way ordinary theory predicts it should, and then, almost unbelievably, regains that superconducting state again once the magnetic field climbs into the range of 40 to 70 Tesla. The superconductivity does not fade gently. It disappears completely as if the material has died and then resurrects itself under conditions that should be even more hostile to it than before. That resurrection is exactly why physicists nicknamed this behavior the Lazarus phase, and the shape this resurrected superconductivity takes is just as bizarre as its timing, forming what researchers describe as a donut-shaped halo that depends entirely on the precise angle at which the magnetic field is applied. Stop and actually sit with how counterintuitive that is for a moment. In every superconductor, physicists had studied for nearly a century, magnetic fields were the enemy, a force that ripped Cooper pairs apart and destroyed the delicate quantum coordination that allows zero resistance current to flow. Engineers designing superconducting magnets, maglev trains, and MRI machines have spent decades working around this fundamental limitation, because stronger magnetic fields have always meant a higher risk of superconductivity collapsing entirely. UT2 flips that entire relationship on its head. Instead of being purely destroyed by strong magnetic fields, this material can be pushed through a kind of superconducting death and rebirth, emerging on the other side in a completely different superconducting phase that only exists because of the extreme field, not despite it. One of the researchers involved in this science publication described observing a metamagnetic transition, a sudden jump in the material's magnetization, and explained that the high field superconductivity only switches on once that transition threshold is crossed, a threshold that itself shifts depending on the angle of the applied field. If this is the kind of content that makes your brain light up, go ahead and hit like and subscribe right now, because we are about to go even deeper into why physicists think this specific material could unlock the most stable form of quantum computing hardware ever built. The reason all of this matters so much beyond pure scientific curiosity comes back to that spin triplet pairing we mentioned earlier. UTE is widely believed to be a spin triplet superconductor, which means the electrons inside it are pairing up with their spins aligned rather than opposed. The exact exotic configuration physicists spent over 2 decades hunting for in strontium ruthenate before that search led to the G-wave surprise instead. In February of 2026, a separate research group at the Norwegian University of Science and Technology announced they believed they had directly observed a triplet superconductor for the first time, calling it the holy grail of quantum technology. The lead physicist on that project stated plainly that materials exhibiting genuine triplet superconductivity represent one of the most sought-after prizes in the entire field of quantum computing, because of their unique potential to host and stabilize those elusive Majorana fermions we talked about earlier. When you combine that triplet pairing with a magnetic field response nobody predicted, you get a material that checks almost every box theorists have been dreaming about for a generation: resilience against the magnetic environments that quantum computing hardware actually needs to operate in, plus the exotic pairing symmetry required to host topologically protected quantum information. Topological protection is the concept that makes all of this worth caring about, even if you have never thought about condensed matter physics in your life. Current quantum computers, the ones built by companies like Google and IBM, are incredibly fragile. The quantum states they rely on can be destroyed by the tiniest disturbance, a stray photon, a microscopic vibration, even a cosmic ray passing through the chip. And this fragility is the single biggest obstacle standing between today's experimental quantum processors and machines powerful enough to solve real-world problems. Topological qubits, the kind that could theoretically be built from Majorana fermions hosted inside a spin triplet superconductor. Like UTE2, would encode information in a fundamentally different way, spreading it out across the material's structure so that local disturbances simply cannot destroy it. Scientists have been chasing this approach for years precisely because it could sidestep the error correction nightmare that currently eats up the vast majority of computing power in every quantum system we have built so far. None of this happened in isolation either, because 2026 has quietly become one of the most productive years in the entire history of superconductor research, almost as if multiple breakthroughs decided to arrive at once. Researchers at the University of Houston announced they had shattered a superconductivity temperature record that had stood untouched for more than 30 years, creating a material that superconducts at a blistering 151 Kelvin, which sounds cold until you realize that translates to roughly minus 122 degrees Celsius, achieved entirely at normal atmospheric pressure rather than requiring the crushing diamond anvil pressures that many previous high-temperature superconductor claims depended on. That distinction matters enormously for practical engineering because a superconductor that only works under extreme pressure is a laboratory curiosity, while one that works at normal pressure and relatively accessible temperatures starts looking like something you could actually build power grids, medical imaging systems, and fusion reactor components around. At almost the exact same time, an entirely different international collaboration called the Super-C Consortium, led by physicist Päivi Torma at Aalto University in Finland, published research showing they had used machine learning to identify two brand new superconducting materials by screening a practically infinite space of possible chemical combinations. The materials, named YRU3b2 and LU-RU3b2, gain their superconducting properties from something called a kagome lattice, a geometric atomic arrangement inspired by traditional Japanese basket weaving patterns, where electrons form what physicists call flat electronic bands. In simple terms, this specific atomic geometry traps electrons in a way that dramatically enhances their tendency to pair up and superconduct. And the fact that artificial intelligence found these candidate materials by narrowing down billions of possible combinations represents a genuine turning point in how superconductor discovery even works. According to Torma, this machine learning approach could eventually push the number of candidate materials researchers can screen into the billions, and the consortium has openly stated its ambitious goal of finding a room temperature superconductor by the year 2033. Think about what a room temperature superconductor would actually mean for a moment, because it is one of those goals that sounds modest until you calculate the implications. Every superconductor discovered throughout history, from the original mercury wire cooled with liquid helium in 1911 all the way through UTE-2 today, has required expensive, energy-intensive cooling systems to reach the ultra-low temperatures, where zero-resistance conductivity kicks in. That cooling requirement is the single biggest reason superconductors have not already replaced ordinary copper wiring in every power line on the planet. A material that superconducts at everyday room temperature without any specialized refrigeration at all could theoretically eliminate transmission losses across entire national power grids, dramatically shrink the size and cost of MRI machines, enable maglev trains that are actually affordable to build at scale, and provide the foundation for fusion reactor magnets powerful enough to finally make commercial fusion energy a reality rather than a permanent 30 years away promise. Now circle back to why the UTE-2 discovery specifically deserves so much attention, because it is not just one more entry on a growing list of impressive materials science headlines. It represents a genuine conceptual break from how physicists assumed magnetic fields and superconductivity relate to one another. For the entire history of the field, the relationship was assumed to be simple and one-directional, stronger magnetic fields. Equal, weaker, more fragile superconductivity, full stop, no exceptions worth building a research career around. UT2 demonstrates a relationship that is not linear at all, but almost cyclical. Superconductivity that dies and returns, shaped into a halo whose geometry depends on field direction, in ways researchers are still working to fully explain mathematically. Now, one of the co-authors on the most recent Nature paper documenting this phenomenon admitted that nearly every new measurement taken on UTE-2 seems to uncover yet another mystery, and that their latest work only begins to explain the mechanism behind some of these strange effects, not all of them. That admission of ongoing mystery is actually one of the most exciting parts of this entire story if you think about it from a research perspective. Physics breakthroughs that come wrapped in a tidy, fully explained package tend to represent the end of a research program, a discovery that closes a chapter. Breakthroughs that arrive alongside open questions and unexplained mechanisms represent something far more valuable, the opening of an entirely new chapter, one that could take a decade or more of follow-up experiments to fully map out. Every major shift in physics history, from the discovery of superconductivity itself in 1911 to the identification of high temperature. Superconductors in the 1980s followed this exact pattern, a strange initial observation that did not fit existing theory, followed by years of scrambling to build new theoretical frameworks capable of explaining it. UTE-2's Lazarus phase looks like it might be triggering the same kind of scramble right now, in real time, across multiple physics departments simultaneously. It is also worth pointing out just how unusual UTE-2 is even before you get to its magnetic field behavior, because the material itself sits in a strand GE corner of the periodic table that most superconductor research had largely ignored until recently. Uranium compounds are considered heavy fermion materials, meaning the electrons inside them behave as though they have far more mass than a normal electron should, due to complex interactions with the surrounding uranium atoms. This heavy fermion behavior tends to produce unconventional superconductivity almost by default, because the strong electron correlations involved create conditions ripe for exotic pairing states that simply cannot occur in simpler metals like lead or tin. Researchers studying UTE2 have also documented signatures of charge density waves and pair density waves in earlier scanning tunneling microscopy experiments, additional exotic quantum phenomena, layered on top of the already unusual superconductivity, although later, more careful studies suggested some of these signatures might be confined to the material's surface rather than existing throughout its bulk structure, a distinction that matters enormously for understanding the true nature of the underlying physics. If you are new to this channel and you want more deep dives that turn cutting-edge physics papers into stories you can actually follow without a PhD, subscribe now, because we cover breakthroughs like this the moment credible research confirms them, not months later once everyone else has already talked about it. The practical roadmap from a laboratory curiosity like UTE2 to an actual functioning quantum computer is admittedly still long, and it would be misleading to pretend otherwise. Growing high-quality single crystals of uranium ditelluride is technically demanding. The material needs to be cooled to roughly 2.1 Kelvin just to reach its ordinary superconducting state before you even start exploring the exotic high-field behavior. And researchers still do not have full theoretical agreement on exactly why the Lazarus phase halo forms the specific shape it does. But every transformative technology in history followed a similar arc, moving from a strange laboratory observation that violated existing theory toward a fully engineered, mass-produced product only after years of painstaking follow-up work. Transistors began as a strange effect observed in germanium crystals, in a Bell Labs notebook before eventually powering every computer on the planet. Lasers were dismissed by some physicists in the 1950s as a solution looking for a problem before becoming essential to fiber optic, internet, surgery, and manufacturing. There is no obvious reason to assume spin triplet. Superconductors and their exotic magnetic field behaviors will follow a different trajectory. What makes this current moment particularly interesting is the sheer convergence of multiple independent breakthroughs happening within the same narrow window of time. You have the Lazarus phase in UTE2 revealing an entirely new relationship between magnetism and superconductivity. You have direct evidence for genuine triplet pairing being reported by an independent Norwegian team. You have Cornell's earlier G-wave discovery in strontium ruthenate, proving that even well-studied, decades-old candidate materials can still hide pairing symmetries nobody had theorized. You have an AI-driven materials screening pipeline out of Finland identifying entirely new Kagome lattice superconductors by processing candidate combinations at a scale no human research team could manage manually. And you have a fundamentally practical breakthrough in Houston, pushing the ambient pressure temperature record higher than it has been in 3 decades. None of these 4 or 5 discoveries happened at the same lab, and none of the teams involved were necessarily building directly on each other's specific findings. Yet together they paint a picture of a field that is accelerating rapidly after decades of comparatively incremental progress. Part of that acceleration almost certainly traces back to how dramatically the tools available to condensed matter physicists have improved. Resonant ultrasound spectroscopy, sensitive enough to detect subtle changes in a crystal's elastic properties at temperatures near absolute zero, simply did not exist in a practical, widely deployable form a generation ago. Machine learning models, capable of screening billions of hypothetical material combinations for superconducting potential, are an entirely 21st century capability, one that would have sounded like science fiction to physicists working in the 1990s. High magnetic field facilities capable of generating the 70 Tesla fields needed to observe UTE2's resurrection phase are massive, expensive, highly specialized national laboratory infrastructure, the kind of instrument that only a handful of facilities on the planet can actually operate. The convergence of better instruments, better computational tools, and a genuinely global, well-funded research community chasing the same prize appears to be compounding on itself, producing breakthroughs at a pace that older, more siloed approaches to physics research simply could not achieve. There is also a broader lesson buried inside this story that extends well beyond superconductivity specifically, a lesson about how science actually progresses versus how we tend to imagine it progressing from the outside. Popular science communication often presents physics as a settled, complete body of knowledge, occasionally punctuated by a dramatic new discovery. The reality inside actual physics departments looks nothing like that. Categories that seem complete and closed, like the supposedly exhaustive list of S-wave and D-wave superconductors, turn out to have entire additional categories hiding just beyond the edge of what existing theory predicted, waiting for someone to build sensitive enough equipment and ask the right question. The Cornell researchers did not set out looking for G-wave superconductivity specifically. They set out to finally settle a 20-year debate about whether strontium ruthenate was a P-wave superconductor. and only discovered G-wave pairing because their data flatly refused to match any of the options anyone had previously considered. That pattern, where the most important discoveries emerge from data that stubbornly refuses to fit existing categories rather than from confirming an existing hypothesis, shows up again and again throughout the history of physics. And UT2's Lazarus phase fits that pattern perfectly. Researchers studying UTE2 were not initially hunting for a superconducting resurrection phenomenon. They were mapping out how the material's superconductivity behaved across a range of magnetic field strengths and directions, following standard experimental procedure. What they found instead, a phase transition, a total collapse of superconductivity, and then an unexpected rebirth shaped into a directionally dependent halo, was not something any existing theoretical framework had specifically predicted in advance. It emerged from careful, patient experimental work, colliding with a material that turned out to be far stranger than anyone initially suspected, which is exactly the kind of story that keeps physicists showing up TO the lab at 3 a.m. chasing one more data point. For anyone wondering where all of this is likely headed over the next few years, the research community's own stated goals give a pretty clear roadmap. The Super-C Consortium has explicitly targeted 2033 as their ambition for identifying a genuinely room-temperature superconductor, a goal that would have seemed almost fantastical just 5 years earlier, before AI-driven materials screening entered the picture. Groups studying UTE2 and its triplet superconducting cousins are focused on the more specialized, but arguably even higher, impact goal of stabilizing Majorana fermions well enough to build the first genuinely topological qubit, a milestone that quantum computing researchers have been chasing since Microsoft first announced a major research push in that direction over a decade ago. And condensed matter theorists, more broadly, are racing to build mathematical frameworks flexible enough to actually explain phenomena like G-wave pairing and magnetic field halos after the fact, rather than continuing to be surprised by experimental results that violate every existing prediction. What ties all of these threads together, the Lazarus phase, the G-wave surprise, the AI-discovered Kagome lattice materials, and the Houston temperature record, is a single underlying message that should genuinely excite anyone paying attention to where technology is headed next. We are nowhere near finished discovering what superconductors can actually do. For decades, the field looked almost mature, dominated by two well-understood pairing categories in a slow, grinding search for marginally higher critical temperatures. That appearance of maturity turns out to have been an illusion created by the limits of the instruments and theoretical tools available at the time, not a reflection of how much strange, unexplored territory remains inside real materials. Every one of the breakthroughs covered in this video happened within roughly the last 18 months, which means the pace of discovery in this specific corner of physics is not just continuing, it is visibly accelerating in real time, right as you are watching this. If a material can genuinely die and come back to life electrically under conditions that should be even more hostile than the ones that killed it in the first place, it forces a certain humility about how much we still do not understand regarding the fundamental behavior of matter at extreme conditions. Physicists spent nearly 70 years operating under the assumption that magnetic fields and superconductivity existed in a straightforward adversarial relationship, one that could be described with reasonably simple equations. UT2 just demonstrated that this relationship can be cyclical, directionally dependent, and capable of producing an entirely new superconducting phase that only exists because of the very magnetic conditions that were supposed to destroy superconductivity altogether. That is not a minor footnote in a physics journal. That is the kind of discovery that reshapes an entire subfield's assumptions and opens research directions that did not exist as recognized possibilities 18 months ago. It helps to zoom out even further and ask why physicists care so intensely about categorizing pairing symmetry in the first place, because from the outside, it can sound like an obscure academic exercise, arguing over whether electrons carry 0, 2, or 4 units of angular momentum when they pair up. The truth is that pairing symmetry determines almost everything practically useful about a superconductor, including how it responds to impurities, how it behaves near its edges and surfaces, and crucially, whether it can host the kind of topologically protected quantum states that make fault-tolerant computing possible. A simple S-wave superconductor like lead is remarkably boring in this sense, useful for certain applications, but fundamentally incapable of hosting Majorana fermions no matter how you engineer it. A D-wave superconductor, the kind found in high-temperature copper oxide materials, behaves differently at its edges than in its bulk, producing surface states that have fascinated physicists for decades, but still fall short of the topological protection researchers actually want. A genuine spin-triplet superconductor, and especially an exotic, higher-order state like G-wave, opens up an entirely different landscape of possible edge states and topological phases, some of which theorists are still working out on paper because nobody expected to need those calculations until recently. This is also a good moment to address something that skeptics of quantum computing hype often bring up, and it deserves a fair answer rather than dismissal. Quantum computing has been described as perpetually a decade away for roughly 3 decades now, and plenty of ambitious claims about breakthrough materials have quietly failed to pan out once independent labs tried to replicate them. That skepticism is healthy and, frankly, necessary in a field that has occasionally overpromised. What makes the current wave of superconductor discoveries different from some earlier hype cycles is the sheer number of independent confirmations arriving through completely different experimental methods. UT2's unconventional behavior has now been documented using resonant ultrasound spectroscopy, high field transport measurements, thermodynamic studies, and neutron scattering across multiple laboratories on different continents, all converging on a consistent picture even while specific mechanistic details remain unsettled. That kind of independent multi-method convergence is exactly what separates a durable scientific discovery from an unreplicated anomaly that eventually fades from the literature. It is also worth understanding just how difficult it is to even attempt these experiments in the first place, because the technical demands involved help explain why discoveries like the Lazarus phase took until 2026 to fully characterize, despite UT2 having been known since 2019. Generating a controlled, stable 70 Tesla magnetic field requires specialized pulsed field facilities, since sustaining that kind of field strength continuously would require more electrical power than most small cities consume. So researchers instead generate an intense magnetic pulse lasting only a fraction of a second and have to take all their measurements within that narrow window, simultaneously cooling a sample down to fractions of a Kelvin while subjecting it to those pulsed fields, and doing so with the angular precision needed to map out a direction-dependent halo represents an extraordinary feat of experimental engineering on top of the physics itself. Every data point in these UTE2 papers represents hours of careful calibration, multiple redundant runs to rule out instrument artifacts, and painstaking cross-checking between different measurement techniques before a research team would even consider submitting results to a journal as prestigious as Science. There's a reason material scientists sometimes describe uranium ditelluride as one of the most demanding compounds in the entire field to work with experimentally, and that difficulty is part of why its full behavior is still being mapped out piece by piece rather than all at once. Growing sufficiently pure single crystals, free of internal defects, requires specialized crystal growth techniques refined over several years, since even minor impurities can mask or distort the delicate superconducting signal researchers are trying to measure. The compound also involves handling uranium, which brings its own set of safety protocols and specialized laboratory infrastructure that most condensed matter physics groups simply do not have access to, limiting the number of labs worldwide capable of producing research-grade samples at all. That scarcity of high-quality material is actually one of the reasons the recent wave of UTE2 papers has generated so much excitement within the physics community specifically, because it means multiple well-resourced international collaborations independently judge this material important enough to justify the substantial investment required just to study it properly. Looking at the bigger picture across all of these 2026 breakthroughs together, there is a compelling case that superconductor research is entering a genuinely new phase of maturity, not because the mysteries are being resolved, but because the field finally has the combined experimental and computational firepower to chase down mysteries that would have simply been impossible to investigate properly even a decade ago. The AI-driven screening approach out of Finland means researchers no longer have to rely purely on chemical intuition and trial and error to identify promising candidate materials, dramatically expanding the search space that can realistically be explored. The pulsed high-field facilities used to study UTE2 represent decades of accumulated engineering investment finally paying off in the form of experiments that were simply not feasible in earlier eras. And the ultra-precise, ultra-cold measurement techniques used at Cornell to uncover G-wave pairing required, building entirely new apparatus, specifically because existing instruments could not reach the necessary sensitivity, meaning the discovery itself was gated behind an engineering achievement as much as a theoretical insight. None of this is to say every open question will be resolved quickly or cleanly. Physicists studying UTT2 still disagree about the precise microscopic origin of the metamagnetic transition that triggers the material's superconducting resurrection, and competing theoretical models continue to circulate without full consensus. Some researchers favor explanations rooted in shifting magnetic fluctuations that reorganize as the field strength changes, while others point toward more exotic scenarios involving multiple competing superconducting order parameters that trade dominance depending on field direction and strength. Resolving that debate will likely require years of additional experiments, more refined theoretical modeling, and quite possibly the discovery of related compounds that exhibit similar behavior in a more easily measurable form. Science rarely moves in a straight line from mystery to textbook explanation, and this particular mystery looks likely to keep physicists busy for a good while yet, which, if anything, only makes it a more interesting story to keep following as it unfolds. Every unresolved detail is essentially an open invitation for the NE, next graduate student, the next postdoc, or the next well-funded international collaboration to make their mark. And given how quickly this specific corner of physics has moved over just the past 18 months, there is no obvious reason to expect the pace to slow down now. Before you go, make sure you are subscribed so the next deep dive into a discovery like this lands in your feed the moment the research becomes public. Because this specific area of physics is clearly not slowing down anytime soon, and the next surprise, buried inside some overlooked material, could be sitting in a laboratory freezer right now, waiting for someone to run the right magnetic field through it and watch what happens.